Welcome to this CompTIA Security AI Plus training series. Throughout this course, we're going to break down the key concepts you need to understand for the exam, while also looking at how artificial intelligence is actually being used in real-world cybersecurity. We'll cover everything from AI fundamentals, machine learning, and deep learning, through to generative AI, language models, prompt engineering, automation, and the security risks that come with using AI. I'll keep each topic clear, practical, and focused on what you actually need to know, with cybersecurity examples along the way to help make the concepts easier to understand. So whether you're preparing for the SecAI Plus exam, building your cybersecurity knowledge, or just want to better understand how AI is changing the industry, this series should give you a solid foundation. Let's get started with Chapter 1, AI in Cybersecurity. In this chapter, we're looking at the main artificial intelligence technologies used in cybersecurity. AI is increasingly being used to detect threats, analyze huge amounts of security data, automate responses, and help security analysts make faster decisions. We'll look at the different types of AI, how AI models learn, how they are optimized, and how generative AI can be controlled using prompt engineering. Traditional cybersecurity systems mainly relied on predefined rules and signatures. For example, if a known malware signature was detected, the system could block it. The problem is that somebody first needs to know what that threat looks like. AI improves on this by learning patterns from data. Instead of only looking for something we already know is malicious, AI can potentially identify unusual behavior that could indicate a new or previously unknown attack. Artificial intelligence is the broadest term we're going to cover. AI describes technologies that allow computers to perform tasks normally associated with human intelligence. This includes reasoning, learning, decision-making, and problem-solving. In cybersecurity, AI can analyze enormous amounts of data, identify potential threats, prioritize alerts, and even automate certain security responses. Machine learning is a branch of artificial intelligence. Instead of programming every rule manually, we give the system data and allow it to learn patterns. Once trained, the model can apply what it has learned to new information. For example, a machine learning model could learn characteristics commonly found in phishing emails and then classify new emails as either legitimate or suspicious. Statistical learning provides much of the mathematical foundation behind machine learning. It uses probability and statistical techniques to identify relationships and patterns within data. For example, logistic regression might be used to estimate whether an email is likely to be spam. Statistical techniques can also help identify unusual behavior in network traffic. Deep learning is a specialized area within machine learning. It uses neural networks containing multiple layers to learn complex patterns. One major advantage is that deep learning can automatically identify useful features from raw data. In cybersecurity, deep learning can identify subtle malware patterns, analyze network behavior, and detect unusual sequences of user activity. This hierarchy is important to remember for the exam. Artificial intelligence is the broadest category. Machine learning is a subset of AI. Deep learning is a specialized subset of machine learning. Statistical learning supports machine learning by providing many of the mathematical and statistical techniques used to understand data. Transformers are one of the most important developments in modern artificial intelligence. They were introduced in the 2017 research paper called "Attention is All You Need." Transformers are extremely effective at processing sequential information, especially text. The most important concept to remember is self-attention. Self-attention allows a transformer to understand relationships between different parts of the input. For example, the admin revoked the user's access because they violated policy. Self-attention can use context to understand that the word "they" refers to the user rather than the administrator. This ability to understand context is one reason transformers work extremely well for language-based security tasks. Transformers have several cybersecurity applications. They can analyze sequences of system events, security logs, network activity, and threat intelligence. Large language models such as GPT are based on transformer technology. GPT actually stands for Generative Pre-trained Transformer. Another well-known transformer model is Google's BERT. Natural language processing, or NLP, is the area of AI focused on understanding and generating human language. Cybersecurity contains huge amounts of text. This includes logs, threat intelligence reports, emails, security alerts, and attacker communications. NLP allows AI systems to analyze this information much faster than a human could manually. Large language models, or LLMs, are trained using enormous datasets and contain large numbers of parameters. Parameters are internal values that allow the model to represent patterns learned during training. LLMs are extremely flexible. In cybersecurity, they can summarize threat intelligence, explain vulnerabilities, analyze security information, and help generate detection rules. Small language models are designed to be lighter and more specialized than large language models. They have fewer parameters and require fewer computing resources. One major security advantage is that an SLM can often run locally. This means sensitive security data does not necessarily need to be sent to an external cloud service. The exam may give you a scenario and ask whether an LLM or SLM is more appropriate. An LLM is usually better when you need broad knowledge and flexibility. An SLM is better when the task is narrow, privacy is important, computing resources are limited, or the model needs to run locally. Remember the main considerations: accuracy, privacy, cost, scalability, and task specificity. One example of something a language model could help analyze is a CVE. CVE stands for Common Vulnerabilities and Exposures. It provides standard identifiers for publicly known security vulnerabilities. For example, CVE-2021-44228 refers to the Log4 shell vulnerability affecting Apache Log4j. An LLM could help explain a CVE in plain language or summarize technical vulnerability information. Another example is Snort. Snort is an intrusion detection and prevention system. Snort rules define patterns or conditions that should generate alerts or potentially block traffic. A generative AI model could potentially help an analyst create a Snort rule from a written description of a threat. Generative AI is different from traditional classification-based AI. Instead of simply deciding whether something belongs to a category, generative AI creates new content. This might include text, images, audio, video, code, or synthetic security data. Two important technologies associated with generative AI are transformers and GANs. A GAN, or generative adversarial network, consists of two neural networks competing against each other. The generator creates fake or synthetic content. The discriminator tries to determine whether that content is real or fake. As they compete during training, both improve. Eventually, the generator can create extremely convincing synthetic content. Generative AI can have several defensive cybersecurity uses. For example, it can generate synthetic network traffic or simulated phishing emails. This can help train machine learning models when real security data is unavailable or sensitive. It can also create realistic phishing simulations to train employees to recognize social engineering attacks. Unfortunately, attackers can also misuse generative AI. AI can create realistic phishing emails, deepfake videos, cloned voices, and other social engineering content. It may also assist attackers in modifying malicious code. Polymorphic malware changes its appearance or structure to make signature-based detection more difficult. So generative AI provides powerful defensive capabilities, but also introduces new security risks. Now we move into how AI models actually learn. There are three major learning approaches you need to know: supervised learning, unsupervised learning, and reinforcement learning. We'll also look at federated learning and techniques used to validate and optimize models. Supervised learning uses labeled training data. This means that during training, the model is given both the input and the correct answer. For example, thousands of emails could already be labeled as either phishing or legitimate. The model learns the differences between them and then attempts to classify new emails. The easiest way to remember supervised learning is learning with a teacher. Supervised learning commonly performs two types of tasks. Classification predicts categories, for example, malware or benign. Regression predicts a continuous numerical value. For example, predicting the number of cyber attacks an organization might experience next week. There are many cybersecurity uses for supervised learning. A malware model might train on files already labeled malicious or safe. An intrusion detection model might train using traffic labeled normal or malicious. Phishing detection can train using known phishing and legitimate URLs. The important point is that all of these examples require labeled training data. Unsupervised learning works differently. The training data does not contain labels or correct answers. Instead, the model attempts to discover structures and patterns itself. This makes unsupervised learning particularly useful when we don't already know exactly what we're looking for. Think of it as learning without a teacher. One common unsupervised learning technique is clustering. Clustering groups similar data together. For example, most employees may have similar login patterns. If one login behaves completely differently, such as a privileged account logging in at an unusual time from an unfamiliar location, the model may identify it as an outlier. This could indicate a compromised account. Another unsupervised technique is dimensionality reduction. Security datasets may contain hundreds or thousands of different features. Techniques such as principal component analysis or PCA reduce this complexity while attempting to preserve the most important patterns. This makes large security datasets easier to analyze and visualize. Reinforcement learning is based on trial and error. An AI agent interacts with an environment and takes actions. Good actions receive rewards. Bad actions receive penalties. Over time, the agent learns a strategy for making better decisions. This strategy is known as a policy. Imagine an AI protecting a simulated enterprise network. The agent might choose to isolate a machine, block an IP address, reroute traffic, or deploy a decoy. If it successfully stops an attack, it receives a reward. If it blocks legitimate activity or misses an attack, it receives a penalty. Over time, it learns which defensive actions work best. This comparison is extremely important for the exam. Supervised learning uses labeled data and is useful when we know what categories we're looking for. Unsupervised learning uses unlabeled data and is useful for discovering patterns or unknown anomalies. Reinforcement learning uses rewards and penalties and is useful for adaptive decision-making. Federated learning is a privacy-focused method of machine learning. Instead of collecting everyone's raw data in one central location, each organization or device trains the model locally. Only model updates are shared. These updates are combined to improve a global model. The original sensitive data stays local. Federated learning is especially useful when organizations want to collaborate but cannot share sensitive security data. For example, multiple organizations could improve a malware detection model without directly sharing confidential logs or malware samples. The model learns from all participants while the raw information remains local. Federated learning does not eliminate security risks. A compromised participant could intentionally submit malicious model updates in an attempt to poison the global model. There are also potential privacy attacks that try to extract information from model updates. So federated learning improves privacy, but security controls are still required. After a model is trained, we need to make sure it actually works on new information. The training dataset teaches the model. A validation set may be used to adjust the model during development. The final test set evaluates its performance on unseen data. The key goal is generalization. We want the model to perform well on new real-world data, not just memorize the training dataset. Overfitting happens when a model learns the training data too closely. It may achieve extremely high accuracy during training, but perform badly when it encounters new information. Essentially, it has memorized the training examples rather than learning general patterns. Underfitting is almost the opposite. The model has not learned enough about the data. This could happen because the model is too simple or has not been trained long enough. As a result, it performs badly on both training and new data. Concept drift happens when the real-world patterns a model learned begin to change. This is extremely important in cybersecurity because attackers constantly change their techniques. For example, a phishing model trained on last year's emails may struggle to detect completely new phishing styles. Models therefore need continuous monitoring and periodic retraining. Fine-tuning takes an existing pre-trained model and trains it further using specialized data. Instead of building an entire model from scratch, we start with something that already understands general patterns. For example, a general email model could be fine-tuned using an organization's own phishing emails. This is a form of transfer learning. An epoch is one complete pass through the entire training dataset. If we train for too few epochs, the model might underfit. If we train for too many, it may begin to overfit. The goal is to find the right balance. Pruning removes parts of a model that contribute very little to its performance. This reduces the model's size and can make it faster and more efficient. This is useful in cybersecurity when AI needs to run on devices with limited computing power. Quantization reduces the precision used to store the model's numerical values. For example, a model might move from 32-bit floating point values to 8-bit integers. This significantly reduces the model's size and computing requirements while trying to maintain similar accuracy. Prompt engineering is the process of designing instructions for generative AI systems. The quality of the prompt has a major impact on the quality of the response. A good prompt clearly explains the task, provides relevant context, supplies necessary information, and may specify exactly how the answer should be formatted. Prompt engineering has many cybersecurity applications. We could ask AI to summarize a long incident report, analyze suspicious logs, explain a vulnerability, or help create detection rules. The more clearly we define the task and provide relevant context, the more useful the result is likely to be. Regex stands for regular expressions. Regex allows us to define patterns that can search or match specific information inside text. For example, we could use regex to identify IP addresses inside a large log file. Generative AI can help create regex patterns, although generated rules should always be tested before use. Yara is widely used by malware analysts. Yara rules describe patterns or characteristics associated with malicious files. They might search for specific strings, byte sequences, or other indicators. Generative AI can assist with creating Yara rules, but analysts still need to validate the output. Modern conversational AI systems often organize messages into different roles. The three main roles we need to understand are system, user, and assistant. Each serves a different purpose. The system prompt defines how the AI should behave. It can establish rules, restrictions, context, and the desired style of responses. You can think of it as the high-level instructions governing the AI throughout the conversation. The user prompt is the direct instruction given to the AI. For example, analyze this PCAP for signs of DNS tunneling. The clearer the task and context, the easier it is for the model to provide a useful response. The assistant role represents the AI's response. In prompt engineering, previous or example assistant responses can also be provided as demonstrations. This helps show the AI what type of output we expect. This becomes particularly important with one-shot and few-shot prompting. Zero-shot prompting means giving the AI a task without providing any examples. For example, summarize this firewall log. The AI relies entirely on its existing training and the instructions provided. Zero-shot works well for straightforward tasks that the model already understands. One-shot prompting gives the AI one example before asking it to complete a similar task. The example demonstrates the expected format or reasoning. This is useful when an instruction alone might not clearly communicate exactly what output we want. Few-shot prompting provides two or more examples before giving the model a new task. The examples demonstrate the pattern we want the AI to follow. In cybersecurity, this could involve showing several examples of safe and suspicious network activity before asking the AI to classify a new event. This is an easy exam comparison to remember. Zero-shot means no examples. One-shot means one example. Few-shot means multiple examples. The more useful examples we provide, the more guidance the model has about the format and behavior we're expecting. Let's summarize the main AI concepts. Artificial intelligence is the broad field. Machine learning is a subset of AI that learns from data. Deep learning is a specialized form of machine learning using neural networks. Statistical learning provides mathematical and statistical foundations used to understand data. Transformers use self-attention to understand relationships and context within sequences. They provide the foundation for many modern language models. Large language models offer broad knowledge and capabilities. Small language models are more specialized, efficient, and can often run locally. For model training, remember these four key ideas. Supervised learning uses labeled data. Unsupervised learning discovers patterns in unlabeled data. Reinforcement learning learns through rewards and penalties. Federated learning allows multiple systems or organizations to collaboratively train a model while keeping raw data local. Models also need to be validated and maintained. Overfitting means the model learned the training data too closely. Underfitting means it hasn't learned enough. Concept drift means the real-world data has changed. Fine-tuning adapts models to specialized tasks, while pruning and quantization make models smaller and more efficient. Finally, prompt engineering is about communicating effectively with generative AI. System prompts define behavior. User prompts define the task. Assistant messages contain the response. Zero-shot uses no examples, one-shot uses one example, and few-shot uses multiple examples. For the exam, make sure you can distinguish between the core technologies. AI is the broadest field. Machine learning learns from data. Deep learning uses multi-layer neural networks. Statistical learning provides mathematical foundations. Transformers use self-attention. and NLP focuses on understanding and generating human language. You should also be able to choose between an LLM and an SLM based on a scenario. Choose an LLM when broad capabilities and general knowledge are required. Choose an SLM when privacy, cost, local deployment, or specialized performance is more important. This is a really useful way to remember the learning methods for scenario questions. If you have labeled examples, think supervised. If you're discovering unknown patterns, think unsupervised. If an agent learns from actions and rewards, think reinforcement learning. If multiple locations train a shared model without sharing raw data, think federated learning. Watch for these clues in exam questions. If training performance is excellent, but new data performance is poor, that's usually overfitting. If performance is poor everywhere, that could indicate underfitting. If the model used to perform well, but becomes less accurate as threats change, that's likely concept drift. Remember what each optimization technique is trying to achieve. Fine-tuning specializes an existing model. Pruning removes unnecessary parts to reduce complexity. Quantization reduces the precision of numbers inside the model to improve speed and reduce resource requirements. And finally, make sure you recognize prompting strategies. Zero shot has no examples. One shot provides one example. Few shot provides several examples. On the exam, you'll likely be given a scenario and asked which approach provides the appropriate amount of guidance. That completes Chapter 1 on AI in cybersecurity. We've covered the foundations of artificial intelligence, machine learning and deep learning, transformers and language models, generative AI, the main training methods, model optimization, and prompt engineering. These concepts form the foundation for understanding how modern AI systems are being used both to defend organizations and to introduce new cybersecurity risks. I hope you enjoyed this video. I'm CyberEd, and I will see you in the next one. Peace.